Okay, yes. Okay, so thank you very much to the organizers for this invitation. I'm very honored to speak at this global seminar. And I would like to share with you some results about topological indices in a geofluid context. So, all right. So I'm not going to assume that you know a lot about this stuff and would like to start with a slow introduction, then present the precise model, and then discuss about the consequence and the properties of this model. So let me first start by some notions about topological insulators, and let's say give you some sort of definition of it. So for me, the original context is independent electrons in a crystal. So you have two equivalent pictures. The first one on the left is called the bulk picture, where you take some infinite spaces. So you have a Hilbert space over the Z2 crystal, for example, L2 of Z2. And you have a self-adjoint operator. Think about discrete Laplacian plus some potential. And depending on the spectral properties of this Hamiltonian, there might exist a topological index, namely a function that associates to Hamiltonian an integer value in a continuous way. And you have to define precisely what it means depending on the problem. And the existence of such a topological index has many consequences. One of it is appearing in the edge picture, where instead of an infinite sample, you take a half infinite one. So the Hilbert space will just be the truncation of the previous one, and the same for the Hamiltonian. What would happen, typically the spectral property is the existence of a spectral gap. At the edge of the sample, this gap will be filled by the so-called chiral edge modes, which would be modes which are confined near the boundary and propagate in one direction. And again, in this picture, you can define a topological index, which is then a locally constant function. And one key property of this theory is the so-called bulk edge correspondence, meaning that the two pictures are fully equivalent, in particular that the two indices coincide, okay? So this was first realized in the context of quantum Hall effect by Hatsugai, and then for discrete electrons in a crystal, there is a theorem by Gian-Michele Graf and Marcello Porta. Okay, so this is a very general story, and you have many realization of it, starting from the original quantum Hall effect measurement, where the plateau you see here are consequences of the topological nature of the problem, and many other features. But these topological indices also appear in other systems, and especially in classical waves. You have an analogy between single particle electrons and classical waves. And the main manifestation of this topological effect is to have edge modes that are really stable. So here on the right, you see some experiment in optical waves. And the main feature of this edge mode that you see here is that they circumvent some defect without any backscattering. So they propagate with a remarkable stability due to the topological origin of the problem. Okay, and these are two other examples in acoustics, in fluids and solid, where you also observe some very stable edge mode, even in presence of a defect. Okay, so these are many examples. There are much more. I'm not going to give a list of it. And this gives you some context. So the question I was interested in this project is what happens for continuous models. So when we go beyond discrete models, in particular, since there is no UV cutoff, then we can have unbounded model. And the question is, do we have a bulk edge correspondence theorem for such model? And as you will see, the answer is more or less yes and no. Now, there is a more fancy question you can ask is, since there are many topological insulators on Earth, then what's the biggest one? And my answer to that is the Earth itself. Why? Well, look at this picture. So these are anomaly temperature at the surface of the ocean, the Pacific Ocean, taken from NASA, and you have one in November and the second one in December. So apart from the blue spot, which is just related to some other phenomenon, the two hemispheres are more or less homogeneous in green. And at the equator, you see this red spot, which is confined at the equator and propagate in a very stable way from west to east. And this phenomenon is called the Kelvin wave. It is known for a very long time. And it appears often, not every year, but I don't remember exactly. But anyway, this is a very stable wave, and you can imagine all the defects that could appear at the surface of the ocean. And one idea of the talk is to show how this can be interpreted as a manifestation of the existence of a topological index. Okay. So,
excuse me.
Yes.
What do the colors mean?
Okay, so this is anomaly temperature. So the red spot will be some excess of temperature. And then you have a fluid relation between temperature and the depth of the fluid. Well, the density, which is related to the depth with some geofluid model. So not directly, this is related to the height of the wave. So you can really imagine that you have a wave which is higher than the rest of the hemispheres. Any other question? Okay, let's move on. Okay, so first of all, we need a model to describe the system and then try to build some topological index from it. So the model is actually quite simple and it's called the Shallowwater model. So what we are describing is a layer of fluid around the Earth, which is very thin compared to the radius of the Earth and also the wavelengths involved. So instead of a 3D model, we will have a 2D model, so 2 dimensions of space, and a 2-dimensional velocity fluid u, which has 2 components u and v. And the third dimension is encoded in some in the height of the layer, okay, and basically some fluctuation eta around some rest frame. So we have 3 degrees of freedom, u, v, and eta. Then the equations that describe this system are very simple. We stay in the linear regime. We have the mass conservation, basically coming from the fact that we work with an incompressible fluid. And then we have momentum conservation. So the acceleration of the fluid is given by the pressure term, which is due to gravity. So this first gradient of eta here. Then we have the Coriolis force, which acts with this u perp, which is simply this given by this expression. And the Coriolis force depends on the latitude. So it would be positive in the North Hemisphere and negative in the South and 0 at the equator. And for those who knows a bit about topological insulator, it will play the role of a magnetic field in a sense. Then we have this strange term, which is called odd viscosity, which also act on this u perp. And we will see its importance later. And let's think about this term as some very small term that is only here for regularization purpose. So we add it for mathematical reasons, but we are not claiming to see it in the ocean, okay? And we'll see why it's important. So let me say a bit more about this odd viscous term before to move on. So this is part of the linear response viscosity term, except that it's antisymmetric. So in particular, this is a non-dissipative term, which is quite counterintuitive compared to usual viscosity. So if you look at the picture below, usual viscosity, when you rotate a solid inside the fluid, then the fluid will have an opposite movement with respect to the cylinder. Whereas with odd viscosity, it would have a transverse reaction. So it's really a strange term, but this is this term is allowed, in particular in dimension 2, if time reversal symmetry is broken, which is the case here because we have the Coriolis force. As I said, this is not a physical effect in the Earth, in the oceanic layer. So for us, it's just a regularizing term. But this odd viscosity also appears in other models. And for example, in chiral active fluids, they managed to have this term with a finite non-zero value. And this has been studied a lot recently. Okay, so this is a reasonable effect, which is actually not present in geofluid, but could appear in some other fields of physics. Okay, and that would be very useful in our construction. So that's for the model. Okay, so now we'll try to build the bulk picture with respect to what I've said at the beginning. And to that, we will, yes, question? Okay. To that, we will simplify the problem as much as possible and start with a translation invariant model. So we will consider a tangent plane at some latitude where the Coriolis force is just a constant parameters. Okay, and so we will work in a plane. And basically, if we come back to, for example, this model and multiply all the equations by I, we have an analog of Schrödinger equation where the wave function, if you like, has 3 degrees, the height of the fluid and the velocity of the fluid. And the Hamiltonian is given by the momentum operator. And it's just a translation of the equation of the previous equations. And we have Coriolis force and the odd viscous parameter. Okay, and this model is very simple because we are in this F-plane approximation where F is a constant. So you can decompose your solutions with normal modes or Fourier transform, or you can look at the symbol of this operator, depending on where you come from. And you are left with an eigenvalue equation where this H is a family of 3 by 3 Hermitian matrices, depending on the momentum Kx and Ky, which are in R2 and unbounded. And then the analog of the energy here is the frequency of the wave, and it's also unbounded. Okay, and this we can solve it explicitly. So let me just show you what are the eigenvalues. We have 3 eigenvalues. It's a 3 by 3 problem. We have these 2 bands with a square root and opposite sign, and then a flat band in the middle, which is always 0. Okay, and here you have a picture of them for small k. And these bands have names from the geofluid context. And the first thing to realize is that when the Coriolis force is non-zero, remember that this is a constant so far, then the 3 bands are separated by 2 spectral gaps, which is the first ingredient to build a topological index. Okay. So let's focus on this case. And otherwise, if F is 0, then the 3 band touch. And this is also an important point. Okay. Now, each band is associated to a rank 1 eigenprojections that we name P plus and minus P0. That goes from R2, where R2 is this parameter space for the momentum, and as a value in the 3 by 3 matrices. And this defines a line bundle over R2. So probably this is obvious for some of you, but let me just remind what I have in mind with this line bundle. So let's focus on the upper band. So you have the eigenvalue equation, the solution of this equation with psi plus, which is a vector in C3, and omega plus is just the frequency band. And you consider the eigenprojection associated to this psi plus, which is a rank 1 eigenprojection. This defines a line bundle, namely over each point kx, ky, you have one-dimensional vector space, and the question is this line bundle trivial or not? Namely, can you deform it to the trivial one or not? And the question over the whole 2D plane is always yes, because this 2D plane is contractible, so the bundle is always trivial. Now, if we look at this odd viscous term, when it's non-zero, then this eigenprojection is actually single valued as k goes to infinity. Namely, its value is independent from the direction where you go to infinity. And so you can actually compactify the problem thanks to this odd viscous term to see the line bundle not over the plane, but over the compactified plane, which is the 2-sphere. And now you have a line bundle over a closed manifold, sorry, S2, and you can ask the question: is this line bundle trivial with with this constraint that that you're on a on a closed manifold? Okay, and the answer it depends, and it is actually encoded in this bulk index, which is called the Chern number. Okay, so this was for the upper band, but you can do it for the lower one and the middle one. And when you have this regularizing term, then the three eigenprojections are indeed single valued, and so you can fully compactify the problem and compute a Chern number for each of them. So you have an explicit formula, which is an integral over S2, and you have this trace expression. And these are topological indices, so you can compute it for P plus, P minus, P0, and you can actually compute them explicitly. So C plus and C minus are given by this expression, where this is just the sign function. So it depends on the sign of the Coriolis force, the sign of the odd viscous parameter, and the flat band is always trivial. Okay, so this is the first index you can build in this problem thanks to odd viscosity. And as I said, the fact that you have a non-trivial Chern number, non-zero Chern number, it indicates the fact that the line bundle is non-trivial, so you cannot find a smooth global eigenfunction. Another thing that is also puzzling here is that if you forget about odd viscosity, then you can integrate this right-hand side over the two-dimensional plane, and this converges and gives you an integer. But this is not a topological index because it's not continuous, okay? So even if you have an integer, it doesn't mean that you have a topological index. So you need really this odd viscous term to define a bulk index. That's the main message of this story. So I'm not giving any proof here, but just to say that the computation is actually simple. And so you can write the Hamiltonian with this spin 1 matrices, and then the eigen projection is just has a simple expression with these matrices and the map here, which is D over D, where D is the parametrization of this Hamiltonian family. And when you have when you have odd viscosity, then this E is just a map from S2 to S2. And the Chern number is basically the degree of this map, namely the times this 2-sphere is wrapping around itself. So if you are not familiar with the previous expression, why this has to be an integer, then maybe this would be more obvious to you that way. Anyway, there is not much more to say there. Okay, any questions so far? So we have this very simple shallow water model. Coriolis force is playing the role of a magnetic field. And if you have odd viscosity, then there is a bulk index. Okay, so this is nice. And the question is, what are the consequences for example, for the picture I've shown you at the beginning? Okay, so the first thing we are looking at are these equatorial waves. Okay, so before we had a tangent plane, Coriolis force was constant, so we were looking locally at some latitude and looking at some bulk properties of the fluid. So let's build an interface instead. So we will just glue two F planes. So F plane means that F is a constant. So in the upper part of the plane, we'll have F positive and constant. And in the lower part, we'll have F negative and constant. This means, remember that this is related to the sign of F. Odd viscosity is the same everywhere. So in the upper hemisphere, the corresponding Chern number would be plus or minus 2, whereas in the lower hemisphere, this would be 0. We have a translation invariant model along X. still, not along y, but along x. So we have normal modes, and we just impose the continuity of the wave function at y equals 0, and also its derivative. Okay, and this is a very simple problem because f is constant in both hemispheres. So we can solve it separately and then glue them together. And here is basically the exact solution. So this is the spectrum of the problem. So you have kx momentum along x, which is a conserved quantity, and omega, which is still the frequency. So you have two colors here. The blue regions are the reminiscence of the bulk bands, namely the solutions corresponding to these blue regions are completely delocalized everywhere in this plane. And on the other hand, you have this yellow curve, which corresponds to solutions which are exponentially decaying away from the interface. And so these blue parts are reminiscent from the bulk 3D pictures I've shown you before, if you project them into the kx omega plane. And in between these gaps, we now have the so-called interface mode that lives at the interface and have a positive group velocity. So they propagate along the equator with a given direction. The one with a linear dispersion relation is precisely the Kelvin wave that I've shown you at the beginning of the talk. And the other one here and here is called the Yanai wave. So now if you focus on a specific spectral gap, so we have 3 blue bands separated by 2 spectral gaps. So let's focus on the upper one, and we see 2 of this interface mode here. And here we have an example of the bulk interface correspondence, namely that if we look here, for example, for some value omega between these 2 blue bands, then the number of interface modes are precisely matching with the difference of Chern number apart from the equator. So here we have +2 minus 0, and that's just 2, which is precisely matching with this number 2. Okay, and the fact that it's topological means that the way you switch from -f to f is completely irrelevant. Here it's convenient because we can compute everything, but we could take any profile from a negative to a positive Coriolis force. We will always count 2 edge modes or interface mode in that case. And in a sense, the message here is that the Kelvin wave that we have seen at the beginning is, how do you say, a consequence of the existence of topological indices. Because here on the upper hemisphere and the lower, you have kind of a topological interface between the two. Okay, so this tells you why this Kelvin wave, in a sense, is so stable and has to propagate anyway. Just a small remark. So I used odd viscosity to define Chern numbers apart from the equator, but you can actually work without it because Earth, I mean, the oceanic layer has no odd viscosity. And these Kelvin and Yanai waves were known for a long time from geofluid people, and they were actually solved exactly for this profile of Coriolis force, which is linear. And so the main new tool here is to say that this has a topological interpretation. Also, in the case of an interface, you can also avoid odd viscosity and define the topological property of the Kelvin wave through spectral flow arguments. Okay, but from what I'm going to say now, this is really important to have this well-defined Chern number. All right, any questions so far? Okay, so that was kind of first part of the talk where you have a nice.
Excuse me.
Yes, sure.
Can you say a few words about the history about the? So Kelvin is a famous physicist. So this was this famous Kelvin who
yes
predicted.
So yes, I know that Laplace is also involved in the let's say discovery of this wave, but it was, I guess, first observed by Kelvin when he was studied how do you say, tidal effect, force de marée, and also this wave was known for a very long time, and I think the simplest model to reproduce this wave was proposed by Matsuno in '66 when he realized that the shallow water model, which is linear, so basically you only need the rotation of the Earth and the change in Coriolis force to make this Kelvin wave to appear. Okay, but okay, I don't know about the full history of this wave,
and
yeah.
Yanai, was more recent, or?
Yes, I guess so. Okay, you caught me on that. I guess the Yanai wave is more recent. It's actually very difficult to observe because it has some asymmetry profile in the velocity, and so it's not that you can like see it directly on the anomaly temperatures like you do for the Kelvin wave. So I think this is more like the last second half of the last century.
Yeah, but still, all these waves have been observed. So
yes, absolutely. The Kelvin, both Kelvin and Yanai wave are observed, and moreover, what I've said is mostly about the ocean, but you also have the same phenomenon in some specific atmospheric layer where the shallow water model is also relevant, and you can see similar phenomena, but they have been observed. Yes.
Thank you.
Any other question about the context or anything, or the mathematics or anything? Feel free to ask. Okay, so as I was saying, this is a nice analogy between quantum mechanics and fluids, and you can use topological ideas to say something about that. But from the mathematical point of view, there is something more interesting, at least for me, and it's kind of the second part of the talk, which is the violation of the bulk edge correspondence here. So here is the new setting. We, instead of an interface, we will consider a model with a sharp boundary. So it's a half infinite plane. So you can imagine that you are locally describing, I don't know, a coast of some continent, for example. And Coriolis force is constant. And the odd viscous term is also constant, positive, and as usual, some regularization parameter. So from now on, the Chern numbers of the bulk bands are fixed to plus or minus 2 and 0, and they won't change anymore. Now we have still a model which is translation invariant. So you can decompose the solution with frequency omega and momentum kx, and you are left with this system of ODE that in principle you can solve explicitly. It's a bit tricky, but you can do it. And the only information you're missing is a boundary condition at y equals 0. And so we will always choose a boundary conditions that keep the problem self-adjoint. So the anomaly doesn't come from going away from self-adjointness. Okay, so all the boundary conditions I'm going to show preserve self-adjoint nature of the problem. Okay, so let's just pick some boundary conditions and look at the spectrum. So the simplest thing to look at is the Dirichlet boundary condition, where both u and v, which are the velocity field component, are 0 at the boundary. Okay, so u is the tangential and v is the normal one. And here is the spectrum. So again, the color code means blue is completely delocalized in the upper half plane, and yellow is confined near the boundary. So here it's not so bad. You have in the first gap, you have two modes. One which is a bit strange because it's saturate at some constant value, but you have two of them, and the Chern number is +2. So if you want to match numbers, so far, there's no issue. But now let's look at this picture. The second condition is called the membrane boundary condition. So V is still 0, and then you have this mixed condition, dxu plus dyv is 0. And then if you solve the problem, then one mode completely vanishes. And of course, we could say, well, maybe it's in the upper part of the spectrum because this band is infinite, but as you will see, it is not. It has really disappeared. And one goal of the talk is to explain why. And now it's even worse if you look at this shear-free condition, which also has this mixed boundary. We would just flip a sign from here to here. Then we see 3 modes, 1, 2, and 3. Again, I'm always focusing on the upper part of the spectrum for symmetry reasons, okay? And this is just a zoom of the central region. Okay, so in the first case, we have 2. In the second, we have 1. And in the third, we have 3. But the Chern number is always the same because it's a bulk invariant. And if we expect the edge mode to be topological, it is a bit surprising that their number depends on the boundary condition. So the rest of the talk is to explain why there is this anomaly and kind of try to quantify that precisely. Okay, so first of all, we need to clarify some issue about counting edge modes. Actually, what's the rule to count the edge modes? Because we have this, for example, mode that saturate at some value, so that there might be some issues. So for that, I will go back to the original counting from Hatsugai, who focus on a single band and count the number of edge modes above and below. So this was in the context of electrons on a crystal. So both energy and momentums are bounded. And you have a band, which a well-defined Chern number in a similar way that what I did. And then you say, if I have some edge mode that merges with the blue bands, then that's +1 below. And if it appears from the band as kx increases, then it is -1, okay? And you have the same rule above, except that you flip the sign. So here it merges with the continuum, so it's -1. And now the bulk edge correspondence is actually stating that the Chern number is equal to the number of edge modes below minus the number above. Okay, so that's our rule or definition of how do you count precisely edge modes. So if we go back to our problem, then for example, in this case, we have one mode, we have one mode here merging with the continuum and another one here, which is also merging. So it's +1, so it's +2. There is no ambiguity and it matches with the Chern number 2. And here you have +1 and that's it, okay? And this way we avoid issue with kind of, if you are familiar with spectral flow counting, which is kind of unstable here. Whereas if you focus on this definition, there is no problem with that, okay? So here you see, of course, the relation states that you have to count the number below minus the number above. But here, the band is infinite, so there is no above. So something should happen at infinity in order for the number of edge modes to change with the boundary condition. Okay, and that's what we are going to investigate. All right, so before to state the main result, I need a bit of definition and theory. So I require a bit of attention. It's a bit technical, but not that much. And I will try to insist only on the ideas and not on the technical details. So the idea is to explore the spectrum through scattering theory and try to look at what happens when we extend this notion at the infinite part of the spectrum. So first of all, what is the boundary condition we are studying? So V is 0, and then we have these mixed boundary conditions for a given value A in R. So previously, if I come back here, we had A equal +1 and here A equals -1. And we are going to study it for every value of A and perhaps see the transition and so on, because it's convenient. and doesn't change much. Okay, so what is our scattering theory here? So kx and omega are conserved quantities, so we can work at fixed value. Then you can look at the solution of what are the ky such that this equation is satisfied, where omega plus is the expression for the upper eigenvalue. In the bulk, this has two real solutions that corresponds to two plane wave, and they are not solution of the edge problem. But if you kind of put them in the edge problem, you see that one has negative momentum in y, so propagates towards the boundary, and this will be the analog of some incoming state. And the other one with positive momentum in y will go away from the boundary and will be our outgoing state. Of course, separately, they are not a solution of the boundary problem, but together we can hope that there is a linear combination of them, which is the solution of the edge problem. And this linear combination will, of course, depend on the boundary condition. Now, with a bit of normalization, you can show that the coefficient appearing in front of the out state is a phase, which is what we call the scattering amplitude. Okay, it depends on the boundary condition, and it also depends on kx and omega, because all this construction is at fixed kx and omega. So this is defined for every value of kx and omega in the blue region. So we can basically explore the blue part of the spectrum in the boundary problem. Okay, so you see it kind of contains both at the same time information from the bulk and information at the edge. So what we are going to do now is to study this scattering amplitude, which is just a phase, along some curve. So here I draw several curves C epsilon. So you start with a small, let's say a small circle in the kx omega plane. And basically epsilon tells you about the center of this circle and its radius. So as you increase epsilon, this will become a bigger and bigger circle. And in the limit where epsilon goes to 0, this will just go to the thick blue line here. Okay, so there is an explicit expression for this curve that you don't need to know. It's just the graphical representation is enough, I think. And we're going to study the scattering amplitude along such curve as epsilon goes to 0. So S is well defined for every epsilon positive, and then we can look at asymptotic quantities. Now we need to do one more step and then we're done. We will split this curve in two parts. One which is close to infinity. So you see as epsilon increases, this is basically, I mean, cut off the drawing, but the circles continue here. And you just exclude a small neighborhood near infinity. And then you have the rest of the curve that I call C0 epsilon. It's just a very simple partition of the curve, okay? But the two will contain distinct information. Okay, so with all that, which is, I guess, was a bit, was a lot, let's see what is the main result. So why is this scattering theory useful? So the first result, basically, we will look at change of argument of this phase along this C epsilon curve. First of all, the first result tells you that you fix any epsilon positive, not even in the limit, and you look at the winding number of S along this curve. And this gives you precisely the Chern number of the bulk problem. So one way to see that is, you see this relates kind of two sections from the bulk, so it's kind of a transition function. Anyway, this winding number along any C epsilon curve gives you the Chern number. So this is, you have the bulk information with the scattering amplitude. Now we will focus at the change of argument along the curve C epsilon, except where we have excluded infinity. So remember that C epsilon 0 is the curve where you have removed some neighborhood of infinity. Now the theorem says that along this curve, the change of argument is precisely the number of edge modes, meaning the number of modes you will see in the spectrum. So for example, here is this yellow branch would be 1. And if you go up enough, you will count all the edge modes. And this is what this result is saying. So as long as you exclude infinity, you see, you count all the edge modes. And now the main result of the theorem is to say these two numbers, C plus and NB, do not coincide. Okay, why? Well, this is the anomaly. So now we look at the change of argument of this, this scattering amplitude along the neighborhood of infinity. So we will have the two pieces together. And here there is a mismatch. So this mismatch depends on the value of A. And remember that choosing A is basically choosing the boundary condition. So for A, smaller than, greater than square root of 2, this number at infinity is actually 0, which is a good news. But the theorem is not only about its value, but it tells you that there is also an edge mode branching precisely at infinity. I'm going to give an example in the next slide. Okay. And the second way it can be anomalous is that this n infinity can be non-zero, so it can be plus or minus 1 for A smaller than square root of 2, but without any edge mode branch at infinity. Okay. So in a sense, there is some anomaly at infinity that counts some edge modes that are not there. So you can call them ghost mode. So I think that the theorem is a bit too big. So let me give you two examples to be much more precise. So here is an example. Remember that the threshold is square root of 2. So below square root of 2, for example, A is 1.25. We see in the finite spectrum, we see one edge mode. Okay, so it's merging here with the continuum. And then the theorem says that at infinity, the scattering amplitude is winding as if there were some edge mode. But we know from analysis of the scattering amplitude that there is nothing else in the spectrum than what you see, namely that this one saturates and does not matter, and otherwise there is nothing else. So there is a mismatch in the bulk edge correspondence because C is plus 2 and the number is 1. Okay, and the mismatch is precisely at infinity. Now, the second way it can be anomalous is above the threshold. So here we see we have one branch here merging, one branch here merging. So it's plus 2. So everything seems fine. And on top of that, the scattering matrix is not, the scattering amplitude, sorry, is not winding at infinity. There is no number. But the analysis of the scattering amplitude tells you that you see this branch that seems to go away is actually going back and merges precisely with the bulk bands at infinity. And so it should be, in a sense, counted as some edge mode. Okay. And so in that way, the problem is also anomalous there because we have, in a sense, 1, 2, and then plus or minus 1 at infinity. Okay, so something is very odd in this problem, and there seems to be a singularity at infinity. Okay, and this also, in particular, it tells you that it's not that you have not plot the spectrum with a big enough resolution that you are missing something. There is really something in the model. All right, so for the rest of the talk, I'm just going to give a few ideas about the proof and where does the anomaly comes from, and then I will just conclude. Okay. So the approach of bulk edge correspondence with scattering theories actually relies on Levinson's theorem. So we are not using this theorem from this slide here, but I think it gives a fairly intuitive idea of what happens. So if you are not familiar with that, originally the Levinsons theorem is about some particle in a radial potential. So this is a 1D problem on the half line where this is the radius. Okay, and pick some potential, which for simplicity, I assume to be smooth and compactly supported, and build the scattering theory in the same way we did. So we have, on the whole line, we have this plane wave that propagate at energy E equals k squared. And when you have a boundary and the potential, you can build a scattering state in the same way. And the coefficient here is also the scattering amplitude. Okay. So you can look at this phase, and usually we take the normalization saying that when we look far away in the spectrum as kappa goes to infinity, then this phase is 0. So this is a phase which is defined up to an integer, so you need to fix a convention to be able to count something properly. Now the theorem says that as you approach the bottom of the continuous spectrum, which would be the one for the Laplacian on the line, then the phase of the scattering amplitudes is proportional to the number of bound states below 0. Okay, so by computing the scattering properties of the continuous spectrum, you can deduce that there exists some bound states. Okay, and this is what we are going to use. And the key to that is actually simple, is that imagine in this equation that you have S that vanishes for some kappa which is imaginary with negative imaginary part. Then you can see that this one is exponentially decaying away from the boundary, and this one vanishes. So you can actually build a bound state from the scattering state up to analytic continuation. So, and that's the main ingredient that we are going to use, okay? So this is the original Levinsons theorem presented in a very vague way, and I'm not going to use it explicitly. And what we are going to use here is a refinement of this theorem by Graf and Porta, where we kind of have a family of Levinsons theorem. So imagine now that for each value of kx here, we can have a similar problem. The free theory in our case would be the bulk picture where there is no edge. And the bound state are the ones which are confined near the edge. And so they are the edge mode. So as you approach the bottom of the continuous spectrum, you can deduce how many edge modes you have. But this is true up to some normalization. So it's not absolute. But relatively, if you follow some continuous parameter kx, you can count the number of edge modes before and after, for example, between these two values, kx1 and kx2. And so you can count, even if you cannot count the absolute value of edge mode, you can count the one that have vanishes or appeared between two values of kx, okay? And so this tells you that the change of argument of the scattering amplitudes actually count what we call the number of edge modes, namely the one that have merged or the one that have appeared, okay? And we can basically adapt this theorem that was for discrete system to our case to show that indeed we can count the number of edge modes we see in the spectrum. Okay, so this is for the non-anomalous part, if you like. And then we can go to the anomaly and actually directly look at the scattering amplitudes at infinity. So you can do some expansion as kx and kappa go to infinity. And here is the explicit shape of this expansion. And you see that the issue here is that you have a square root of this 2kx squared plus kappa squared. And remember that one of the key ingredients for Levinson's theorem to work is analytic continuation. But if you go through that with this conical singularity, then you will have kind of a problem because this will induce two Riemann sheets when you go to complex value. And because of this singularity, you actually decouple the change of argument of the scattering amplitude with the presence of edge modes. And that's why at the infinity, we are counting something that is not there, or we are not counting something that is there. And now if you inspect carefully what happens in our problem, you see that there is a threshold, and that below or above, you have two different scenarios where one edge is present, but S is not winding, or the opposite, okay? And usually in Levinson's theorem, you always say that at infinity, everything is trivial, and you use it as a normalization. And here that's actually not possible because there is the anomaly. All right, so let me just conclude and give you some very short perspective with this project. So to summarize, there is a nice analogy between geofluids and single particle quantum mechanics, which helps you to give the interpretation of stability of Kelvin wave as a consequence of a topological interface. Main ingredient being to have a change of Coriolis force in the two hemispheres. And one technical assumption is to assume the existence of this odd viscous term to have well-defined Chern number. Okay, and this explains somehow the stability of these equatorial waves. Now, even if it's possible to define a well-defined Chern number, even if you stay with a self-adjoint boundary condition, even if you give you a precise way of counting edge modes, there is a violation of bulk edge correspondence, okay? Because the number of edge modes will drastically depend on the boundary condition. And this is due to some conical singularity at infinity in the scattering amplitude formalism. So if you are not familiar with fluids, or if you think this is a specificity to fluids, well, let me just mention that it's actually not the case at all. And you can play the same game with the Dirac Hamiltonian, okay? So that would be the spin 1/2 analog of the previous problem, which was more a spin 1 problem. So here is the massive Dirac Hamiltonian. And again, we have this regularized Dirac Hamiltonian. And this is actually very standard to regularize Dirac Hamiltonian that way. And it's actually what inspired us to play the same game with a geofluid model. And then we realized after all that it was odd viscosity. Anyway, if nu is non-zero, so if the model is regularized, then the two bands have a well-defined Chern number, which is given by this expression. So for m and nu positive, you have plus or minus 1. Sorry, plus or minus is missing here. And now if you look at the spectrum of this problem, then there are some boundary conditions where everything goes well, such as Dirichlet. So this is a 2x2 problem. So the wave function is psi1, psi2. And now there are some fancy boundary conditions, still self-adjoint, where the number of edge mode is 0 and the Chern number is +1. So it has completely vanished. And the same analysis with Levinsons theorem can be pursued. And you see that indeed you have the same kind of anomaly in the infinite region of the spectrum. Okay, and this anomaly is really symptomatic of this unbounded spectral bands, and you can actually do this for any 2D model with arbitrary spin. All right, so let me just mention people I've worked with. So Pierre Delplace and Antoine Venaille from Lyon, and Michele, Graf and Hansueli from Zurich. And if you want to read in a popularized way this story, I really recommend this last reference, which is in French, but very well written. And with that, I think I'll stop and thank you for your attention.
Thank you very much. It was really interesting. Are there questions?
May I ask a question?
Gian, yes.
Behind all of this there are some versions of the Levinson theorem. So the classical Levinson theorem is about, as you said, about one-dimensional Schrödinger operators, scalar Schrödinger operators.
Yes.
Now, in your case, you have a vector, you have a differential, a one-dimensional differential operator acting on vectors on three with three components. So this is not exactly a Schrödinger operator, but something similar.
Yes.
So how far one can generalize the Levinson theorem to such operators, and have it been worked out? Okay, so a good question. So first of all, we are not really using Levinson's theorem directly, but basically you reprove everything in a different context, and it works for this vector version of Schrödinger operator. So I think for the original Levinson's theorem, it should work too with a bit of work, and I think this has not been investigated as far as I know. But I think this should work the same. But yeah, it will. Yeah, it will depend on many. I mean, in your case, that this operator, it contained the second derivative. Yes. But not everywhere. So can you? Yes, it's more. My operator. Can one describe the structure, the property of that is relevant for some kind of Levinson theorem or Levinson-like theorem? Mm-hmm. So, okay, I think my operator is more like a Dirac type operator, and the second order is a regularizing term. So I think what we should look for is a Dirac version of Levinson's theorem, and then maybe some extension for the Schrödinger case with internal degrees of freedom. You see, one thing important here, maybe here, is that even though I have a vector solution, I only have one incoming state and one outgoing state. So the scattering amplitude is just U1. It's not a matrix, even though the problem is a vector. So I think how is it possible? So I mean, you have 3 degrees of free. Yes, but so what happens with the other? I think because that's just because the scattering theory is a pure analogy, in the sense that this in and out state are eigensolution of the bulk problem at fixed value of kx and omega, and so it is a rank 1 eigenvalue. So the way I define the scattering theory is very different from the usual one, I would say, and so this way I only have one-dimensional incoming states and outgoing states, and so I'm not sure we are really exploring the vectorial nature of the problem here. So perhaps it's actually close to the original Levinson's theorem in that sense. So somehow you threw out the rest of the components, and you compressed your problem to one component problem, or? Yes, I reduce it to a one component problem with a very specific prescription, being that they have to be eigenvalues of some of the bulk problem, and so it is a kind of artificial one scalar problem on top of this vector case, I would say. And this artificial scalar problem, can it be understood as a differential problem? That's a very good question. And if so, of which degree? So it's kind of some effective theory. Well, I would say of order 2, because I have this this odd viscous term is non-zero everywhere. It's small, but and if this odd viscous term is 0, what changes? Well, for the scattering theory, I don't know. That's a good point. It should work too. But right, the point is really we are really in between
order 1 and order 2 because the order 2 term is off diagonal in a sense. It's a non-dissipative effect. Well, you see, because of the vector nature, the Laplacian term are not a diagonal term. So I'm not sure. Yes, it's difficult to put it in some specific Schrödinger problem that way. But I could investigate first without odd viscosity, right? That would be probably easier and see if there is a connection with some effective operator in 1D.
Thank you.
Thank you.
Thank you. Other questions?
Yes.
Halle,
So yeah,
yes.
it was very interesting. Thank you. So
Thank you.
I'm curious about the stability of this anomaly, the violation of bulk edge correspondence. So do you sort of have to fine tune your boundary condition to see this anomaly, or is it somehow stable?
Okay, a very good point. So I don't know. Do you still see my screen? No, probably not.
No,
Okay,
I
sorry.
see you. But
Okay,
yeah.
well, it's less interesting. Do you see it now or?
Yes, we do.
Okay, so as you see, the anomaly is studied for this family of boundary condition. So, and the anomaly is here for all the values of A, basically.
Okay.
So it is stable at least on a one-dimensional line. So now what I'm doing currently is to work with the Dirac Hamiltonian, and I'm trying to provide a classification of all the boundary condition and look at the anomalous one. And there seems to be the same way one or two parameter family which are always anomalous, and other big family which are completely anomaly free. But
do you think you can propose experimental setup that you see this anomaly?
I wish. So I think with geofluids, it's not within reach because of this odd viscosity term. But this regularized Dirac Hamiltonian appears in superfluid helium description. And M would be, I think, the chemical potential, and nu would be the mass of the helium atoms, I think. So there might be a physical realization. And now the question is, can you find a decent boundary condition for this problem?
Yes.
And so far, I don't know. I wish.
Very interesting. Thank you.
Thank you.
Thank you. Other questions? So I just have one naive question. So you are looking at water waves, and
yes.
Why not air waves as well? I mean, to describe the climate.
Okay, so
because situation should be quite similar. It's also a fluid,
yes.
It's also 2D, it's also very thin.
So actually, as I said, this model actually describes atmospheric layers too. And the Kelvin wave is also observed above the ocean. The only thing is here, I'm basically cheating because I'm taking a very simple model from the fluid point of view. You see, it's linear, first of all. And so if you want to go with a climate effect and precise atmospheric effect, then you have to go to nonlinear. And then the question of topology is much harder. So in a sense, you have to look for simple models that appear in a geofluid context where you can basically plug your topological theory. But this was done for other models too, and probably in fluids this could occur too. You don't need much to produce it. Yeah.
Thank you. Are there further questions?
Yes, I have two questions.
Yes, please.
Okay. Hi, Clement.
Hi, Jacob.
Thank you for the talk. So the first question is, why do you compactify it all? Because I thought you could calculate the Chern number in real space on R2, for example, for Landau Hamiltonian, you don't need momentum space, and you could just use the double commutator formula in real space without compactifying. And the second question is, how exactly would you characterize what is necessary for this violation? For example, you showed a counterexample of Dirac operator, which is unbounded spectrum. could there be ever a counterexample of a Schrödinger operator that has only half infinite spectrum?
Okay, so thank you for the two very interesting questions. So the first one, so it indeed continuous model and topology, it has been known for a very long time with the Landau Hamiltonian. The main difference is with Landau Hamiltonian, you focus on a finite energy region. You take either one band or several, but it's always finite in energy. So in a sense, this cutoffs helps you to have a well-defined Chern number. And here the compactification is needed because you can explore a large region of the spectrum in energy. So it's not because it's over the 2D plane, but it's because you access to infinite energy through this plane. And so this is why you need the compactification. And if you do not, if you naively compute Chern number, then you get something which is discontinuous because you can always contract the full plane to a point, and then it would be 0. Okay, so are you happy with this answer, or?
The last sentence confused me because, I mean, for Landau Hamiltonian, you could also use this logic.
No, okay, no, I'm talking about the momentum plane, not the real space plane.
Uh-huh.
So here, if you compute the Chern number in the momentum plane, then you can contract it to 0 and always get 0. Whereas if you are on the 2 sphere, you can have non-trivial values. And I think if you would like to use the double commutator formula here, you will need some argument to say that the operator is trace class. Then we will kind of need a cutoff in energy, which appears in the Landau Hamiltonian because you only select a few bands. And there is somewhere where the trace class properties require some cutoff in energy, which you don't have here. So I would say that the problem is not trace class in real space here because of that.
Okay, thank you.
And the second question is about I think, so for this kind of anomaly to appear, the way I detect it is to have a singularity at infinity. So first of all, you need a spectral band which is infinitely extended. So it could be a model that is bounded from below, but has an infinite extended spectral band. And then I think one ingredient for the anomaly to occur is to have an X derivative in the boundary condition, because then it brings a Kx, which can go to infinity and kind of mess everything. But yeah, this is just speculation so far.
So a Schrödinger operator that has half infinite spectrum, but where at least one band has no gaps, extends to infinity.
Yes, exactly. Yes, precisely. Yes.
Which I don't remember. There was some Sommerfeld conjecture that was proven. Yeah. Okay.
Okay. So you say perhaps it does not exist.
I'm not sure. But
okay.
Other people must know better.
Okay. Good point.
Thank you.
Thank you. Any other questions?